electrochemical series. So by measuring the potentials of different electrodes with respect to the reference electrode, which is standard hydrogen electrode, in short SHE. So in this way we can make a series of standard electrode potential, and this series is known as electrochemical series. Now there is international convention that the standard potential of electrodes, they are tabulated for reduction half reaction. Okay, so reduction half reaction, it means that the tendencies of the electrodes to behave as cathode towards SHE. Now if it is very that is the tendency of the electrode to behave as cathode, that means it will accept electron and it will be reduced, so SHE then must be anode. So if this tendency is very high, then the reduction potential value, that will be very high. Now for SHE we know the E value that we consider is 0.0 volt. So if the tendency of the electrodes to behave as cathodes towards SHE is very high, then it will have positive value for electrode potential. And if the tendency of this element with respect to SHE to behave as cathode, that is the tendency of the element to get reduced, if this tendency is very low, then the value will be negative. So in that case SHE will be cathode and the other system, that will be anode, because it has tendency to feed electron to other system but not itself get reduced. Okay, so in this way we have electrochemical series. So there will be hydrogen, which is standard hydrogen system, H plus H2 system. This is standard, having electrode potential 0.0 volt. On one side there will be all the positive values of electrode potential, and on the other side there will be all the negative values of electrode potential. So element which has higher reduction potential, it will get reduced easily. So in that case it will be cathode and SHE will be anode. While the elements which has lower reduction potential, it will get oxidized easily. That means in that case SHE will be cathode and the system, that will be anode. Electrode with positive E naught values for reduction half reaction do in fact act as cathode. That is the values on that side of the SHE where all the values are positive, so they will behave as cathode versus SHE. While the negative E naught values of reduction half reaction, they will behave as anode versus SHE. So from the chemical that is electrochemical series, suppose we have taken the system Ag plus Ag, and for this the reduction potential value is 0.8 volt, and for SHE we know it is 0.0 volt, and for another system nickel 2 plus 2 nickel, so we will write always the oxidized species first, because these values are reduction potential value. So for reduction half reaction we are having all these reduction potential values in the electrochemical series, so that is why it is written in this way, and this value is minus 0.26 volt. Now with respect to SHE, if we connect it with this system, then this will be cathode and SHE will be anode, because this value is higher than 0. Similarly, if we are connecting it with the nickel system, then this will, as it is negative value, so it will behave as anode, and in that case SHE will behave as cathode. Okay, so in this way from electrochemical series we can check all these values of reduction potential of all the system, and we can easily predict that which system will be reduced and which system will be oxidized, that is which one will be anode or which one will be cathode. Okay, so these are the importance of electrochemical series. So we will see now that what are the different applications of electrochemical series one by one. The first application is reactivity of metals, that is which metal will be more reactive, which metal will be less reactive, because there are in the electrochemical series several metal electrodes, their reduction potential values are given. So alkali metals and alkaline earth metals, that is the metals from group 1 and group 2, their reduction potential values are highly negative. So that means they are having high tendency to feed electron, that is they will lose electron and they get oxidized. So they can react with cold water. Even they can react with cold water. Even hot water is not necessary. Their tendency to lose electron is so high that they can even react with cold water and evolve hydrogen. So it means what? In water, oxidation state of hydrogen is H plus. But now, after the reaction, it is evolving hydrogen. That means now oxidation state of hydrogen is 0. So from +1 it is reduced to 0. That means this reduction that is done by these alkali metals or alkaline earth metals. So they can react even with cold water, and they have the capacity to reduce H plus to H0. So first there will be hydrogen atom formation, and 2 hydrogen atom they will form H2. They can also readily dissolve in acids, forming corresponding salt. So suppose we have any alkali metal or alkaline earth metal, M plus or M2 plus, then if we are treating it with any acid, suppose HCl, then in HCl H is +1. So metal, what it will do? Now it will replace this H and it will form the corresponding salt, that means MCl. And if it is HNO3, it will be MNO3. If it is H2SO4, it will be M2SO4. Okay, and hydrogen will be evolved. So they readily dissolve in acid, forming corresponding salt, that is MCl, and they can combine with those substances which accept electron. Which accept electron means those substances, they are actually oxidizing substance, because these metals are that is, they are itself very good reducing agent. Okay, so these are the one category of metals. They are very reactive towards water or acid. Now there is another category. Now for this category, here we have this list. You can see all these are group 1 and group 2 metals. They can react violently with cold water, and within this, all that is within alkali and alkaline earth metals also you can further classify them in 2 sections, because cesium, francium, rubidium, those who are in the down the group more, they will be more reactive. So that is why, though all of them are alkaline and alkali metals, but still among them there is also variation of reactivity. So for sodium, lithium, barium, radium, strontium, calcium, moderate reaction with cold water and strong reaction with hot water or steam. So for the first point, this is basically this table. Okay, but within this table also there is variation of reactivity. The next category is iron, Pb, Sn, nickel, cobalt, etc. They do not react with cold water, but with steam they can react. That means now we have to provide more energy, then only they can react. That means their reactivity is lesser compared to the previous group. So only then, that is, if we provide steam, then only they can provide hydrogen, but cold water there will be no reaction. So this second type, this is moderately reactive. So moderately reactive, among them again there is some variation. That is magnesium, very slow reaction with cold water, strong reaction with hot water or steam. Then we have aluminium, titanium, manganese, zinc, iron, moderate reaction with hot water or steam and dilute acid. And nickel, tin, lead, slow reaction with dilute acid. So among these, all are moderately reactive, but still there is some variation. So magnesium is maximum reactive, then these metals, and then nickel, tin and lead. And the last one, so these points, it is the second one, this, and metals like copper, silver and gold. So you can understand, silver, gold, they are very stable at room temperature. That's why we can use ornaments made of silver and gold. Okay, so these are very unreactive. They lie below hydrogen. But remember, this below, this word better we do not use, because it is relative. Because in some books you can find that the electrochemical, it is given in such a way that the negative values are written above hydrogen and the positive values are given below hydrogen. And in some cases you can also see the reverse case, that is positive values are lower, that is below hydrogen, and negative values are above hydrogen. So this below and above, this is relative, but just remember that copper, silver, gold, their reduction potential value, it is towards positive side. That means with respect to sheet, their tendency to oxidize other system, that is very high. So their reducing tendency is very low, they are very less reactive, they will always try to remain in zero oxidation state. So that is why silver and gold, they are so stable, and they do not they are less reactive and do not evolve hydrogen from water. So in the previous category, moderately reactive, we have seen that if we increase the temperature of the water, that is steam or hot water, then there will be reaction. But now the last category, they are so unreactive that even they cannot react with hydrogen, they cannot evolve hydrogen from water even if it is steam. So the least reactive category, do not react with cold water, no question. So even hot water, steam, there is no reaction. So you can understand this is so unreactive. And with dilute acid also there is no reaction. So these are the three main categories of metals. So from the electrochemical series, we can easily identify by looking at the values of reduction potential that which metal will be more reactive. That is, we can compare different systems. This is the first application. Now the next application, electropositive character. Now you can find some similarity with the previous point, that is, higher is the reactivity, higher will be the electropositive character. So we know that alkali and alkaline earth metals, that is group 1, group 2 metals, they are more electropositive. That is, the metals that are in the left hand side of the periodic table, they are more electropositive compared to D block elements or the metals that are present in P block. Okay. So electropositive character of the metals we can check from electrochemical series, and the thermal stability of their oxides, that is metallic oxides. So like reactivity, electropositive character of metals decreases from top to bottom in the electrochemical series. So top to bottom, this line is only correct if the positive values, positive reduction potential values is below hydrogen and the negative values above hydrogen, then only this line will be correct. Otherwise it will be opposite, that is bottom to top. Okay, so you have to just remember that if it is very electropositive character, that means the reduction potential mode negative. So higher, that is more is the negative, the reduction potential, higher will be the electropositive character. So better than you remember in this way, that is top to bottom or bottom to that is opposite direction. It is better you remember that reduction potential, in which case reduction potential is more negative, that means it is more electropositive. As the electropositivity decreases, the thermal stability of their oxides, that also decreases. Now why it is so? Suppose we have any oxide of M2+. So its oxide will be MO. Now in MO, the oxidation state is 2+. But as electropositive character is less, that means the metal will always try to remain in metal 0 state. So that is what, but if the metal oxide is very stable, that means what? This 2+ oxidation state must be stable. But as that electropositive character is, when it is decreased, then the tendency of the metal to remain in 2+ state or any other state, that is very less, and they will try to accept electron from other system and will be reduced to M0. So that is why when electropositivity decreases, thermal stability of the oxides also decreases. That means if you heat this oxide, it will be easily decomposed to metal 0. That is, oxidation state will be easily changed to metal 0. The oxides of metals of having high positive reduction potential obviously are not stable towards heat. So high positive value means electropositive character is less. So don't think that high positive reduction potential value means high electropositive. No, it is opposite. When the reduction potential value is highly positive, that means the electropositive character is very low. So that is why the oxides are not stable towards heat. The metals which come below copper form unstable oxides. That means these are decomposed on heating. Now below copper means, again I am saying that below copper, or it may be written as above copper, because different places you can find different types of arrangement of the reduction potential electrode. Sometimes it starts from negative value, then 0, then positive, and sometimes you will find that positive values are first written, then 0, then negative. So below and higher compared to copper, it is not important, but the important thing is, suppose for copper the value is actually Cu2 plus Cu, this value is 0.34. So if it is more positive compared to 0.34, that means their oxides will not be stable. That is the meaning of this line. So they will decompose if we heat these metallic oxides, because their tendency to remain in the oxidized state is very low. They will always try to accept electron and convert it to in zero oxidation state. So again here we have a table of 3 different types of metals. You can also compare it with the previous reactivity series that we have seen, that is moderate reactive, highly reactive, and less reactive. So here we have this category, which is it is already mentioned that if the metals having reduction potential value near about -2 or more negative means suppose -2, -2.5, -3, like that, you will mostly find these negative values for alkali metals and alkaline earth metals. So that is why they are strongly electropositive in nature. Then for the intermediate category, the moderately electropositive metals, the values are ranging from 0 to -2. That means -1, -1.5, -1.8, all these values. So they are moderately electropositive. These are the example. So they can react with hot water or steam. This category they can react, remember in the last slide we have seen the first application, they can react even with cold water. And weakly electropositive metals, the metals which below hydrogen and positive, again see below hydrogen, this is only true if the positive values are below hydrogen, but you can also remember it in this way, that the metals which are having positive values of reduction potential, that means for hydrogen it is 0, so it will be +1, +2, +2.5, like this. So these positive values when you are seeing, then you will understand that they are weakly electropositive metals, that is copper, silver, mercury, etc. So they belong to this group. So they will not react with steam, that we have seen in the last slide. So here we have 2 examples of metal oxide. So as we have seen that metals which come below copper, that is more positive value than copper, they will form unstable oxide. So silver oxide, you can see weakly electropositive. Here we have silver and mercury. So mercury oxide and silver oxide, if you heat it, then it will reduce. Now here it is having +1 oxidation state, mercury +2 oxidation state, it will reduce to silver 0 and mercury will reduce to Hg0. Okay, so in this way we can also predict from the electrochemical series that whether the corresponding metallic oxides they will be stable or unstable. Here we have a problem which is regarding this electropositive character. The position of some metals in the electrochemical series in decreasing value, they are mentioned in this question. Okay, magnesium maximum electropositive, and silver is minimum electropositive. So what will happen if a copper spoon is used to stir a solution of aluminium nitrate? Now aluminium nitrate means what? Aluminium, we know it's stable oxidation state 3+, and nitrate anion is NO3 minus. So aluminium nitrate, its formula will be AlNO3 because it is 3 plus. Okay, so oxidation state of aluminium in this nitrate salt is 3 plus. Now if in this solution of aluminium nitrate, suppose we are dipping a copper spoon. Now that means that copper, it is in metallic state, that is 0 oxidation state. So aluminium is +3 state and copper is in 0 state. So if there is any reaction or not, that we have to predict. Now if you look at this decreasing order, then aluminium is more electropositive than copper, right? It is greater than copper. That means aluminium has higher tendency to give electrons towards other system and copper has tendency to accept electron. But here that is not possible because it is already in 3 plus oxidation state. So here we cannot expect any reaction. Now look at the options. The first option is saying that the rod was coated with aluminium. What is the meaning of this line? That copper will be coated by aluminium. So for that, aluminium must be converted to 0. But it has very low tendency to accept electron from other system, then the rod cannot be coated with aluminium. Next is an alloy of copper and aluminium was being formed. This is not correct. The solution turned blue in color. That means it is trying to say that copper can be oxidized to Cu2 plus by aluminium. Okay, but aluminium cannot oxidize copper because it is more electropositive, so it will always try to feed electron to other system. So it cannot accept electron from copper. So ultimately what it means that there will be no reaction. But suppose if you are doing the opposite thing, that is, suppose you have copper nitrate solution and you are dipping a aluminium spoon, in that case there will be reaction. Okay, because aluminium, it will feed electron and itself will be converted to 3 plus, and copper, it is in +2 state because you have taken copper nitrate solution. So copper 2 plus will accept electron and it will be reduced to copper. So this reaction is not possible. So that means the opposite reaction, reverse reaction is possible. Okay, so correct option will be option D. The third application, displacement reaction. So displacement reaction, you can understand. Here we have this general representation. Suppose we have A and another compound of B and C, these two elements. So after reaction, what is happening? B is replaced by A. So now we have AC and B. So this is the displacement reaction. Okay. So we can predict from electrochemical series whether a given metal, it will displace another metal from its salt solution. That means the metal that will displace, this metal will be in 0 oxidation state, and the metal which is present in its salt, it will have some positive oxidation state. So when it is displacing, suppose A, it is in neutral state and B is having oxidation state +2. So when A is combining with C, that means A now is +2 and B is 0. That means A must be more electropositive compared to B, then only it can give electron towards B and it can reduce B. So this process, it is oxidized, that is oxidation reaction, and from +2 it is converted to 0. This is reduction. So the metal having low standard reduction potential, that means more electropositive, the values are towards negative side, they will displace the metal from its salt solution which has higher value of standard reduction potential. Okay, here we have example. We have two systems, Zn system which is converted Zn2 plus, that is better we write in this way, that Zn2 plus Zn system and copper 2 plus copper system. Now if we compare the reduction potential values, copper 2 plus copper system has higher reduction potential value. That means this species will accept electron from the other species. That means Cu2 plus will accept electron from Zn. So here copper, it is present in its salt form because it is Cu2 plus. Suppose if it is copper sulfate. So in the beaker we have copper sulfate. That means copper having oxidation state +2. Now we have dipped this zinc strip. Now zinc strip means it is in zero oxidation state. So gradually what will happen? The blue color of copper sulfate, now it is reduced. Why? Because gradually the copper 2 plus ions are converted to Cu. So this process is reduction and this process is oxidation. Okay, so that is why now metallic copper that is deposited in the surface of the zinc strip and Zn sulfate will be formed, because now Zn is oxidized to Zn2 plus state, so it will form Zn sulfate. So gradually in the medium, solution medium, it will be Zn sulfate, and this zinc strip gradually it will be reduced in size because zinc is converted to Zn2 plus, so it will not be in the metallic form. So the strip that will be gradually reduced in size. Fine. Another type of displacement reaction, displacement of hydrogen. So under displacement we will see that there are different types of displacement. In this case you have seen one metal is displacing another metal. This is one type of displacement. Second type of displacement is displacement of hydrogen from dilute acids by the metals. So the metal which can provide electrons to H plus ions present in dilute acid, because in dilute acid there is presence of H plus. Suppose you have taken HCl, so there is H plus, but if this H plus is accepting electron, it will be converted to H, and two hydrogen atom together it will make H2. That means there will be evolution of H2. So hydrogen will be evolved from dilute acid, but it is possible if the metal is highly electropositive. Now if you look at this picture, here we have magnesium acid, zinc and acid, iron and acid. So in the first case the reaction is very vigorous because magnesium is maximum electropositive. So electropositive character is Mg, then Zn, then iron. Okay, so reduction potential value, it will be opposite. It will be maximum for iron, then zinc, then Mg, because it is opposite relation. Okay, higher is the reduction potential value, higher is the tendency to get oxidation. So magnesium and acid mixture, there is evolution of hydrogen and the reaction is very vigorous. In the second case, the reaction is occurring in moderate rate. Here also hydrogen is evolving, but the reaction is not so vigorous as in the case of magnesium and acid mixture. And in case of iron, the reaction is very slow. Fine. So it proves that the displacement of hydrogen from dilute acid by the metals, it will occur at different rate for different metals. So which metal will react fast, that we can understand from the electrochemical series, because we can check the reduction potential values and accordingly we can understand that in which case hydrogen will be evolved very readily or very slowly. The third type of displacement is regarding non-metal. So in this type, it is a displacement of one non-metal from its salt solution by another non-metal. Okay, so until now we have discussed only mostly about the metals, and we write the system as M plus then M. But now when we are talking about non-metal, obviously positive oxidation state is not possible. So now for the non-metal, suppose if it is X, then it will be written as X, X minus, or X2, half X2, X minus, because this is, in case of metal, this is the oxidized state, this is the reduced state, so that is why it is written first. But now X0 is the reduced state, oxidized state, because compared to X minus, this is oxidized state. Here we have more electron, here it is zero oxidation state, so it is represented in this way. So the non-metal which possesses high positive reduction potential, obviously they will accept electron. That means they will act as oxidizing agent and they will displace another non-metal with lower reduction potential. So here we have, suppose we have taken three systems: chlorine, bromine, iodine. That means half chlorine Cl minus, it is having more value of reduction potential than half bromine Br minus, and which is having more value than half iodine and I minus. That means chlorine can oxidize bromine and iodine. Actually it can oxidize Br minus and I minus, but it cannot, that is, if we take bromine, it cannot replace chlorine because it is having lower reduction potential values. So if you look at this table, here we have all these halogens. So suppose, and in the right hand side we have KCl, KBr solution and Ki solution. So you have added chlorine to KCl, there will be no reaction because it is the same system, right? But when you have added chlorine to KBr, that means chlorine it is in 0 oxidation state, and Br it is in -1 oxidation state. That means chlorine can accept electron from bromine and it will oxidize Br minus to bromine. So there will be liberation of bromine gas. Okay, that means you have started from KBr plus Cl2, but now after the reaction we are getting 2KCl plus bromine. So Br minus is replaced by chlorine. Okay, so now we have the salt KCl. KBr is no longer present, and if you are adding chlorine to Ki, it is having even lower value than bromine. So obviously here reaction rate will be more compared to the previous one. So now I minus is replaced by Cl minus. So that is why we have started from Ki, but now we are having KCl and iodine will be report. Similarly, if you have taken bromine and you are adding it to KCl, there will be no reaction because bromine is 0 oxidation state, but here KCl, Cl is negative oxidation state, but bromine cannot accept electron from Cl minus and itself is reduced by Br minus because it is having lower reduction potential value. So that is why there is no reaction, and it is the same system, so that is why reaction here not possible. But Br minus can bromine can accept electron from I minus, so that is why now Ki is converted to Kbr and it can evolve hydrogen. And at last we have taken iodine and we are gradually adding it to KCl, KBr and Ki. But in these two cases, last one obviously there will be no reaction because it is the same system, but it cannot convert Cl minus and Br minus to the corresponding 0 oxidation state, that is chlorine gas and bromine gas, that is not possible. So that is why there is no reaction. So it proves that from the electrochemical series, in the non-metal side, it is not about the metals. In the non-metal side, if we look at the reduction potential values, you can understand that the system which is having high positive reduction potential value, as we have here chlorine which is having more positive value compared to bromine system, it will accept electron readily. That means it has a high tendency to act as oxidizing agent. Okay, so this is a third type of displacement under displacement reaction category that we have seen. Now the fourth type is displacement of hydrogen from water. We have already seen displacement of hydrogen from acid, but now instead of acid, reaction is occurring with water. Here we have taken two examples, iron and sodium. Now we know that iron is less electropositive compared to sodium, and obviously the reduction potential value of iron, is greater than reduction potential of sodium, but sodium is more electropositive, right? So that is why here you can see that water we have taken in liquid form. So liquid water, sodium can react. But in case of iron, it is in gaseous state. That means you have to take hot water or steam. Otherwise, there will be no reaction with iron, because iron is less electropositive compared to sodium. So iron and the metals having more negative electrode potential, they are capable of liberating hydrogen from water. So it is the limit point. That is, if you move further iron, that is, if you are moving towards the positive side, there will be no reaction with water. But if you are moving to another direction, that is iron and the metals having more negative electrode potential, they will be capable of liberating hydrogen from water. So mostly these metals are alkali metals and alkaline earth metals that can liberate hydrogen even from cold water. But they can liberate hydrogen from hot water or steam. So that is why here physical state is different. Okay. And here sodium is converted to Na plus, and here iron from zero oxidation state. This is actually mixed oxide. It is mixture of Fe2O3 where oxidation state of iron is 3 plus, and FeO where oxidation state is plus 2. That means iron from zero state, now it is converted to plus 3 state and plus 2 state. That means it is oxidized. So in both cases metal is oxidized, and H plus is converted to H0. That means it is reduction. Okay, so that is all about displacement. So different types of displacement are there. Metal is displacing metal from its salt solution. Metal is displacing hydrogen from acid. Metal displacing hydrogen from water, and non-metal displacing another non-metal from its salt. Okay, different types of displacement. The fourth point is extraction of metals. So in metallurgy, we know that a more electropositive metals, it can displace a less electropositive metal from its salt solution. That we have already seen. So this principle is actually utilized in the extraction of silver and gold by cyanide process, because these two are that is reactivity for these two is very less. Their electropositive character is very less. So that means it can be extracted from its salt solution. So silver from the solution containing sodium argentocyanide, that is this one, NaAgCl2, it can be obtained by the addition of zinc, because it is more electropositive than silver. So here we have, here the reducing agent is actually Zn, and Ag, it is already in plus 1 state. Okay, because cyano is -1, so 2 cyano means -2. And how it is balanced? Because for both this metal there is +1 state. So silver, it is in +1 state and it has high tendency to accept electron from Zn. So Zn from 0 state, now it is converted to +2 state. So see here we have 2 positive charge from sodium, 2 positive charge from Zn. That means total positive charge is 4 plus, and we have 4 cyano minus. So it is neutral. So zinc is oxidized to +2 and silver is reduced to silver 0. So this principle that more electropositive metal, it can displace the less electropositive metal, that is zinc is displacing silver, this principle it can be utilized for the extraction of metals. Okay, so suppose we have any metal ore where the metal is present in some particular oxidation state. Then if we are treating that with more electropositive metal, then the more electropositive metal will feed electron this less electropositive metal, and it will be converted to in metallic form, that is 0 oxidation state. So in this way, extraction of metals, of less electropositive metals by the high electropositive metals, that is possible. The fifth point, corrosion treatment. We know that there is a tendency of corrosion in some metals, so we can prevent it by some method. So how we can do it, that we will see here. But before that, we have to understand very well what is corrosion actually. So corrosion is the chemical process of deterioration of metals. So here we will basically focus on, there are different types of corrosion, but mainly we will focus here corrosion of metals. So of this, the most important by far is electrochemical corrosion of metals, in which oxidation process, that is metal from zero state, it is converted to positive oxidation state. It is not necessary it is +1, it may be +2 or +3, and it is facilitated by the presence of suitable electron acceptor. So metal is converted to oxidized state and it is leaving this electron. That means there must be some agent which can accept this electron, and very good electron accepting agent which is available in environment is oxygen. Okay, so that is why here suitable electron acceptor, that is oxygen. Here we have a picture, and this is iron, that means it is in zero oxidation state. Fine. Now in the iron surface, suppose there is this type of that this surface is not smooth, but here the surface is smooth. Okay, so where the surface is not smooth, that is very narrow space, here oxygen cannot reach very easily. So it acts as anodic site, and the smooth surface, which surface can be easily in contact with oxygen, that surface is acting as cathodic site. Fine. So this electron, as here oxygen presence is low in the anodic site, so this anodic site, that is the same iron, one side of iron is behaving as anode, another side of cathode, this is another side of iron that is behaving as cathode. So the smooth surface which is in contact with oxygen more, that will be cathodic, and the surface which is not in contact, yes, it is also in contact with oxygen, but compared to the smooth surface, it is less in contact with oxygen. So that is why the electron that is removed here from this iron, that is iron is leaving electron, this electron can be reached towards the cathodic side where the amount of oxygen is very high, and this oxygen can accept this electron and it can be converted to it can be reduced, because here it is zero oxidation state, but in water oxygen having oxidation state -2, so this is reduction. So in cathodic side reduction is taking place. So gradually what will happen, iron will gradually be converted to Fe2+, that is oxidized, that means corrosion is going on. Now this Fe2+, in presence of oxygen, it can be converted to Fe2O3, where oxidation state is +3. That is further oxidation of Fe2+ to Fe3+, and this with some molecules of water, that is known as rust. So in this way the metal surface can be corroded. So the surface which is acting as anodic side, the more time is with time, what will happen, the corrosion will be more here, that is further this narrow surface, it will increase in size. So a very common way by which we can protect this corrosion, that is how we can prevent this corrosion, is protecting steel, which is nothing but iron, from corrosion, is to coat it with a thin layer of zinc. Now why we have chosen zinc? Because zinc is more electropositive than iron. So obviously when zinc coating is present over iron, suppose there is zinc, so now zinc is in presence of oxygen, so oxygen will prefer zinc compared to iron to accept electron, because Zn has high tendency to give electron towards some electron accepting species compared to iron. So that is why zinc coating, this process is also known as galvanizing, because that is the zinc coating that is present on the iron surface. The process by which it is done, it is known as galvanizing. The zinc coating being less noble than iron. Less noble than iron means less noble means less unreactive. Noble means it is unreactive. It tends to corrode selectively. So dissolution of this sacrificial coating. Sacrificial coating means because it is sacrificing itself by giving electron towards oxygen. So the sacrificial coating leaves behind electrons which concentrate in the iron. Now what happens? the zinc has more tendency to donate electron. So these electrons will be deposited on the iron surface, and as a result, what will happen? It will make it more cathodic. More cathodic means, as here number of electrons is very high and cathodic side is always reached with electron because here reduction occurs. So that is why it will become more cathodic and thus inhibiting its resolution. So now corrosion will be restricted. So in this picture, in first case there is layer of zinc. Fine. So zinc is converted to Zn2 plus. There is presence of iron. There is presence of electron. So this negative charge in iron inhibits the dissolution of iron. But suppose instead of zinc coating, if you have done tin coating, now iron is more reactive than tin. Zinc is more reactive than iron, but iron is more reactive than Sn. So what will happen? If we do coating with tin, the corrosion process will enhanced further, because now tin also has high tendency to accept electron. So as if now oxygen is already there to accept electron, now tin is also there. So here we do not have any substance which can act as sacrificial agent. There is no one to sacrifice electron. So tin will accept electron, it will not sacrifice electron. So that is why now the corrosion, it will enhance. Okay, so you can see corrosion is more here. So in this way, by applying a coating of more electropositive metals on iron, we can prevent the corrosion. Okay, so this is also application of electrochemical series. Now the sixth application, this is very important, and you will find numericals regarding this application very frequently, that checking the spontaneity of a redox reaction. So suppose some overall reaction is given, or here you can see some cell representation is there, which is nothing but one type of galvanic cell. This is a Daniell cell actually. So whether this process is spontaneous or not, that we can predict from electrochemical series. So spontaneous reactions, remember spontaneous reactions, it will always have positive potential. So for half reaction, what is the corresponding E naught, that is for Zn2 plus Zn? We know what is the reduction potential, which we can find from electrochemical series. And for the other half reaction, that is copper 2 plus copper, that also, that is the E0 value also we can find from electrochemical series. Now we know how to calculate the overall electrode potential. It is, first we will take the reduction potential in the cathode system, and in the cell representation in the right hand side always cathode is present, left hand side anode. Here oxidation is going on, here reduction is going on. Okay, so what we do, we find E naught of the cell by E naught of right hand side, that is cathode, and E naught of left hand side, that is anode. So if this value is positive, that means it is spontaneous. But if this value is negative, the reaction is not possible. So suppose some overall reaction is given and the corresponding reduction potential values are also given, and if it is asked that predict whether this reaction is spontaneous or not, you can easily find it out by doing this calculation. And sometimes this type of cell representation can also be given. So here in the left hand side, the reaction that is going on is zinc converted to Zn2 plus, it is sacrificing 2 electron, and in the right hand side copper 2 plus is accepting electron and it is converted to copper. Now we will do this calculation. So let's see what are the values from this electrochemical series. So for Zn2 plus Zn system, the value is minus 0.76, and the other system, that is copper 2 plus 2 copper, this is plus 0.34. Actually, even you don't have to do the calculation, just by looking at these two values you can easily understand whether this reaction is possible or not, because it is more electropositive. So it will be acting as cathode and it is already in cathode side, and you can, if we do the calculation, it will be 0.34 minus 0.76. So this minus will be positive, so obviously this value is positive. So this reaction is spontaneous, right? But suppose the cell representation that is given in this way, that is CuS copper sulfate aqueous salt bridge, then Zn sulfate aqueous and zinc electrode. So if it is asked that for this cell representation, is it possible? So you will find the E naught value. So E naught cell, it will be, first you have to write the right hand side value, which is minus 0.76, and then you will write the left hand side reduction function, which is minus 0.34. So this value is highly negative, so this reaction is not spontaneous. So in this way we can check the spontaneity of a redox reaction. Okay, here we have a problem. The standard reduction potential value for some system, that is Zn, nickel, iron, these three given. Okay, this is for Zn, this is for nickel, this is for iron. Now the reaction X plus Y2 converted to X2 plus and Y, that means Y2 is reduced, Y species is reducing to Y from 2 plus 10, and X is oxidation. This is oxidation, this is reduction. So we have to predict here that this reaction it will be spontaneous when different XY systems are given in options A, B, C, D. Okay, so when it is X is nickel, it means what? That iron Y is reduced. That means when you will calculate the E naught cell, first you will take the value of iron minus 0.44, and then we will take the value of the other system, which is for nickel. Now this is, it will be positive, sorry, it will be this minus will be positive, but ultimately this is negative because this value is high. So here, as it is negative, this is not possible. Then the next one, now X is same, now Y is Zn, that means E naught cell will be, for zinc it is minus 0.76, then minus 0.23, so this will also be negative, so this is not possible. Next, now our X is Fe, Y is same, so we will write Y system's reduction potential first and then iron. Now for iron it is minus 0.4, so this will also be negative. So the correct option must be the last one because it is single correct answer. Now Y is nickel, that means we will write this value first and then for Zn. Now for Zn it is minus 0.76. So see, this is positive. You don't have to do the full calculation, you just need the sign whether it is negative or positive. So this is positive, which is clear from this expression, right? So correct option will be D. So the reaction is Zn plus Ni2 plus, then Zn2 plus and nickel reduced. Okay, so this reaction is possible. Option D is the correct option. In this way we can predict in which case there will be spontaneous reaction. It is the last reaction. Here a cell representation is given. One side we have M system, another one is X system. So E naught for the M system is minus sign, sorry, 0.44 volt, and for the X system it is 0.33 volt. So from this data we have to predict which option will be correct. This is also single choice correct answer. So in the first case, both M and X in zero oxidation state, and after the reaction M is M plus. That means M will accept electron. Sorry, M will give electron towards X because X is reduced to X minus and M is oxidized to M plus. Okay. So for this reaction, even you don't have to consider the cell representation. You just have to check which system is reducing, which system is oxidizing. So here X is reduced to X minus. This is reduction. M is oxidized to M plus. This is oxidation. Okay. So E naught cell, how we can find? It will be E naught of X system first, that is 0.33. I am simply writing X and E naught for M system. So it is 0.33 minus 0.44. So see, this is negative. That means this reaction cannot be spontaneous. Now, if A is not spontaneous, obviously B should be spontaneous. So without going to C and D, that is my advice is how you can save your time during exam. So when you are saying that A is not spontaneous, obviously this has to be spontaneous. So this must be the correct. Suppose if you have very less time in your hand, you can easily choose this answer. But we will check it here. Now M plus is reduced to M. So this is reduced and X minus is oxidized to X. So this is oxidation. So now E naught cell, we will write the reduction side first, which is 0.44 and 0.33. So this is 0.11. So it is not 0.77 or minus 0.77. The value is, that is ultimate, the E naught cell value that is mentioned here, which is not 0.77, even not minus 0.77. So this is 0.114. And suppose if it is multiple correct choice answer, then there may be one of this option, it may be 0.11. Then we will choose that both option B or another option is correct. But here it is single choice, so option B will be the correct option. Okay, because here the value is positive, so it is spontaneous, but this is not spontaneous. Okay. Now this is multiple corrected. For the reduction of MnO4 minus to Mn2 plus. So why it is reduction? Because here the oxidation state of Mn is plus 7, which you can easily calculate. Suppose this is how to calculate it. Suppose Mn having oxidation state X and oxygen, you know, per oxygen it is minus 2. So minus 2 into 4, overall charge is minus 1. So X must be 7. So from plus 7, now it is reduced to plus 2 state. For this system, E naught given 1.51. And the reduction potential for this 4 system, it is given as, this 4 system it is given. Now which of these metals will be oxidized by MnO4 minus? That means among this 4 metal system, which can reduce MnO4 minus to Mn2 plus. That means which can make Mn plus 7 state to Mn2 plus state. That means it has to donate electron, right? Now look at the values of this Mn system. I am simply writing Mn. It is 1.51, right? Now for Zn it is minus 0.76. Then for silver it is 0.799. For gold it is 1.69, and for sodium it is minus 3.0. So now look at the values. This is acting as oxidizing agent and all these have to act as reducing agent. So how it can act as reducing agent? It must be lesser value compared to the value of 1.51. Now among these 4 system, in which case we have lesser value? We have lesser value in case of zinc, in case of silver, not in case of gold. It is greater than 1.51. But here also it is possible. So it is possible for zinc, silver and sodium. That means zinc, silver and sodium. So correct option will be A, B, D. But it is gold cannot reduce manganese +7 state to manganese +2 state. It is not possible by gold. It is only possible by Zn, silver and sodium. Okay.